Hello everybody, and we'll be looking at the first experiment. In the weighing with different balances, you're supposed to know the various balances that were supposed to be used in the experiment, one of which is the triple beam balance. You have to know that. Then we have top loader, balance. Then finally we have the analytical balance. So I don't know if most of you are with your manual. These are the three balances that you were supposed to use in experiment 1, and I went through most of your manuals. You guys were all reporting off from what you're supposed to report. Okay, now I'm going to explain the triple beam balance and when to use it, what values or what measurements can be used for the triple beam balance, right? So you can see on the screen here, this is what a triple beam balance looks like, which we have in the lab. So basically, the triple beam balance is used for measuring weights whose accuracy is limited to plus or minus 0.1 gram. All right, that is for the triple beam balance, meaning that it can measure weights such as 4 gram, which is equivalent to 4.0 gram. All right, that means it can measure weights such as 25 gram, which is equivalent to 25.0 gram. You can go on and on again. It can measure weights such as 150 gram, which is equivalent to 150.0 gram. So if, for example, your calculations fell in this decimal placement, it means that the instrument that can be used to measure that quantity of sample is triple beam balance. All right, so if you get to look at your manual, you were supposed to calculate some amount in grams of different samples. So if, for example, your answer was 5 gram, which is the same thing as 5.0 gram, this is telling you that the suitable balance to measure such weight will be the triple beam balance due to its accuracy being limited to plus 0.1. It is more convenient. But then these are balances that we no longer use as much, due to advancement. But the essence of the experiment was for you to know the differences and the decimal placements and the accuracies of these measuring instruments or weighing balances. Okay, so that is about triple beam balance. We'll also do the calculations. So but then let me wipe this off. Then let's look at the next weighing balance. Now you have to understand that the triple beam balance, all right, the triple beam balance, the top loader and the analytical balance, they are all weighing balances. All right, they are all weighing balances. So don't go about, most of you don't know their names actually, but these are their names: triple beam balance, top loader, and the analytical balance. So let's go to the top loader balance. The top loader balance measures, its accuracy is limited to 0.01 gram. See, triple beam balance is 0.1, top loader is 0.01 gram. So it means that it can measure values such as 5.25 gram. Can you see? These are the decimal placements you can see here. All right, so, and it can measure values such as 4.0 0.65 gram. Can you see? It can measure values such as 7.10 gram. Understood? So it can measure values such as 7.05 gram conveniently due to its accuracy being limited to plus 0.01 gram. That is for the top loader balance, which you can see on the screen too. So now it means that if you have any calculation that falls within this decimal placement, can you see 2 decimal places? So it means that the suitable balance is the top loader. All right, so let's go to the next balance, which is the most precise. It is used for taking precise measurements. All right, when accuracy is very much at its peak, so you need an analytical balance. So the analytical balance can measure weights whose accuracy is limited to 0.1234, 0.001 gram. Can you see? So that means its accuracy is very high and is very much precise. It's used for taking precise measurement. All right, so that means if you derive or you have a value such as 6.2845 gram and you want to measure such weight, an analytical balance is preferable. Can you see the 4 decimal places just after it? All right, so that means you need an analytical balance. You want to measure a value such as 3.1423 gram. You will need an analytical balance. Can you see that? So this is used for measuring. Analytical balance serves for this purpose. All right, now let's go into the calculations you were asked. All right, let's go into the calculations right now. So in your calculations, you are asked to calculate the amount in gram of 0.1 mole sodium hydroxide, right? And that was basically it. All right, how would you calculate 0.1 mole sodium hydroxide? All right, now this is where you have to employ your formulas. All right, if you are asked to calculate the amount in grams, so that means you don't know the amount in grams. All right, so but there's a general formula which says that number of moles equals to mass in gram divided by molecular weight or molar mass. So this is the formula to use, right? So now you look at the question. Number of moles is given as 0.1 mole. This is number of moles. So number of moles is given as 0.1. So you have 0.1 equals to mass in gram. Mass in gram is what we are asked to find. So I'm going to denote that with an X because we don't know it. Then divide by the molar mass. Molar mass of what? The molar mass of sodium hydroxide. So we have molar mass of sodium hydroxide. We have to calculate that. Sodium is 23 plus oxygen is 16 plus hydrogen is 1. So if you add all this up, you have 40 gram per mole. Now you have to know the units. All right, molar mass, the unit is in gram per mole. Unit for mass in gram is gram. Unit for mole is mole. You get it? So I have to put this value here. So it's going to be x over molar mass is 40, so I have s over 40. Right? So this is 10 over 1. So I'm going to cross multiply. So that means x equals to 40 multiplied by 0.1, which is 4.0 gram. Now looking at this value, 4.0 gram, can you see that and someone gets to ask you, what measuring instrument or weighing apparatus can be used from the experiment you've conducted, from the exposure of the different weighing balances we have. Now, can you guess or tell me what weighing balance is suitable for the measurement of 4.0 gram? The answer is pretty simple. We've earlier said previously that the triple beam balance has its accuracy to plus 0.1 gram. The top loader balance has its accuracy to 0.01, that's plus or minus 0.01 gram. Then that of the analytical balance 0.12, 3 even up to 4 gram, right? So now look at it. This value is more likely to be this. So that means this value can be measured using the triple beam balance. So that is the answer. Can you see that? It's that easy. So if, for example, your calculation was 4.65 gram, you definitely know that the instrument or the weighing apparatus that could be used is the top loader. So, but if it was, beyond this, it is the analytical balance. So this is how you calculate the mass in gram of any compound, right? So get used to this. These are some of the questions you see in your CBT, and you have to be very fast in doing it. So let's do one more example. Then you'll be the one to tell what balance to be used. Let's say you are asked to find the mass in gram of 0.133 mole of benzoic acid. If you are asked to find the mass in gram of 0.133 mole of benzoic acid, what is the first thing you do? Now remember that number of mole equals to mass in gram divided by molar mass, right? And you are asked to find the mass in gram, which is this one. So that means you are supposed to know your number of mole. We have to know our number of mole. We have to know our molar mass, since we need to know the mass in gram, right? So what is the number of mole from the question? 0.133. So I have 0.133 will be equals to X, which is mass in gram, divided by molar mass of what? Of benzoic acid. What is benzoic acid? C6H5COOH, right? Carbon is 12, so I have 6 multiplied by 12 plus 5 multiplied by 1. All right, so basically we have another carbon plus 12 plus 16, that's oxygen is 16, so we have 2 of that, which is 32 plus 1 hydrogen over there. So when you sum all of this up, you should have 122 gram per mole. So you substitute it here, 122. So all you have to do, cross multiply. Now X will be equals to 0.133 multiplied by 122, which is 16.226 gram. Can you see that? Now someone would ask you, what weighing apparatus will be used to take precisely the weight of this sample? Now, can you answer that question? If you can answer that correctly, then you should know that it is the analytical balance. analytical balance, and that is right. So this is how you calculate mass in gram. All right, be sure to always know the unit you're working on. Unit for number of mole is mole, unit for mass in gram is gram, unit for molar mass is gram per mole. All right, so that is that. Let's go to experiment 2. So experiment 2 was titled primary standards and the preparation of standard solutions. So first off, you need to know what a primary standard is. Primary standard, and you need to know what a secondary standard is. All right, now what are primary standards? These are substances that are very much high purity that are used to prepare solution of known concentrations. All right, so they are very much of high purity. They serve as reference standard solutions. Okay, then we have secondary standards. Now these secondary standards are not as pure as the primary standards. Okay, they are standardized against primary standards, which means they are substances whose concentrations can be known by employing a primary standard. So for you to determine the concentration of a secondary standard, you need a primary standard as a reference point. All right, so there are substances whose concentration must be known by employing what we know as the primary standards. All right, but they are all standard solutions. And what is a standard solution? Solution of known concentration. So you should know this. So we'll just look at the calculation aspect of this experiment. Now I'll use an example, only one example, that should assist you in knowing how to do these calculations, and that will be calculate the amount in gram. Calculate the amount in gram of 200 centimeter cube 0.01 molar sodium triisonitrate 5. So this is what we'll be looking at. Calculate the amount in gram of 200 cm cube 0.01 molar sodium triisonitrate 5. Now what you should look at here is look at the values: 0.01 molar volume, look at the compound in question, all of this, and look at what you're asked to find. All of this will give you an insight for your calculation. All right, so now if we look at this one, let's start with this. The first one, amount in gram, means we are going to find the amount in gram, right? So we have this one, which is volume. We know this is volume, right? So this is what? 0.01 molar. We know this is molarity. Molarity. And if we see this, it means that we are going to calculate molar mass. All right. Now, in the case of this, we are not going to be using number of moles equals to mass in gram over molar mass. Can you see that? This formula will not hold because what we have here is number of moles and not molarity. Can you see? And not molarity, even though we have the mass in gram, right? And we have molar mass, right? So this formula will not hold. The formula to solve this sort of calculation is molarity equals to mass concentration over molar mass, right? This is the formula to use, and you have to know that you have to know the units. The units are very important. The unit for molarity is capital letter M, or mole per dm cube. That is the unit for molarity. The unit for mass concentration in the previous formula is gram, because mass in gram, right? But in this formula, the unit for mass concentration is a concentration mass, right? It is gram per dm cube. Now, what is the unit for molar mass? It has always been what it is. So it's gram per mole. You have to know this unit very, very well. Now, since we've identified the formula we are going to use and why we are using the formula, let us now include our variables. Molarity equals to mass concentration over molar mass, right? What's the molarity? This one. Remember the unit, capital letter M, or mole per dm cube, like I previously said. So I'm going to have 0.01 equals mass concentration. What does it mean? Gram per dm cube. We don't have that. All right, so we have X. Can you see that? We don't have that because we don't have any value that has, let's say, 4 gram per dm cube. None of our values have this unit, so that's why we don't have that. Okay, so we call it an X. Now the molar mass, you have to calculate the molar mass of sodium triisonitrate 5, which I said each time you see the formula, chemical formula, know that molar mass is involved. So sodium is 23, nitrogen is 14, plus oxygen is 16. That means 3 multiplied by 16. All right, so if you sum this up correctly, you should be having 85 gram per mole, right? So you go ahead, substitute it here as 85. Here you cross multiply, right? This is 1, cross multiply. So x times 1 is x, right? 0.01 times 85 is 0.85. So I have 0.85. What is the unit for mass concentration? Gram per what? dm cube. All right, can you see that? So this is the difference between mass in gram unit and mass concentration unit. Mass in gram unit is gram, but mass concentration unit is gram per dm cube. So know the difference. All right, so once you've been able to arrive at this stage, remember we want to find the amount in grams. So now we have to now break down this answer. What does this answer mean? It means that 0.85 gram is in 1 dm cube. This is per dm cube means 1000 cm cube. Can you see that? That's what it means. So now, but the question is asking you how much in gram will be in 200 cm cube. So I'm going to put x will be in 200 cm cube. So what then follows is that I'll cross multiply 0.85 multiplied by 200, 170 equal to 1000 multiplied by x is 1000 x. Now you divide both sides by 1000, divide both sides by 1000. So when you divide this, you should have 0.17, right? Remember amount in gram. So this is the amount in gram in what? 200 cm cube. So you can put per 200 cm cube, all right? Or you just leave it that way. But this is the amount in gram. So the amount in gram in 200 cm cube is 0.17. I guess this is clear enough. So this is how you solve such questions. If you see it, definitely you will see it in your CBT, and you have to know these formulas and how to use them and know their units, because you might see a question where you have same answer. For example, you have I guess I can wipe this off. Answers that were presented were 4.0 gram, 4.0 gram per dm cube, cube. Then you had 4.0 mole per dm cube. And for example, you were asked to find the mass concentration. If you don't know that this is the right unit for mass concentration, you are going to fail. Option A, option B, option C. So if you see such question, always know the right unit for what is being asked. Experiment 3 is titled Standardization of Sulfuric Acid using sodium triisocarbonate 4. Now you should ask yourself, what does it mean? What does it mean to standardize? To standardize means to find the concentration of that particular substance. So if you're standardizing sulfuric acid, it means that you are trying to determine the concentration of the acid. So if you are standardizing H2SO4 using sodium triisocarbonate 4, so it means that you are trying to determine the concentration of sulfuric acid using this one, meaning that sulfuric acid is the secondary standard. Remember, we've defined that. And the sodium triisocarbonate 4 is the primary standard. You see, that was why we defined secondary standard as substances whose concentrations can be known by employing a primary standard, because they are not as pure as the primary standard. So standardization means to determine concentration of that particular substance. All right, so in this experiment, you are supposed to know how to balance the equation of reaction, right? So it's a neutralization reaction, meaning that you're going to form a salt, sodium tetrasulfate 6 plus water plus CO2. Then you tend to balance it. It's pretty easy. So also learn how to balance chemical equations. This is S, all right? So we have 2 sodium here, we have 2 sodium here, 1 sulfur here, 1 sulfur here, 4 oxygen plus 1, 5, this 4, 6, right? We add 4 and 2 is 6 plus 1, 7. How much do we have here? 4 here and 3 here, making 7. Can you see that? Hydrogen is 2 here. You see hydrogen is 2 here, hydrogen is 2 here. So it's balanced. This is quite a direct one. Okay. So, and there is one particular calculation we'll look at. Right? It's important. You also know how to do that, even though we've shared insight in the previous experiment. All right. So, and that calculation is, how would you prepare preparation of let's say 100 cm cube of 0.05 molar sodium carbonate, sodium triisocarbonate 4 solution. So how would you prepare 100 cm cube of 0.05 molar sodium triisocarbonate 4 solution? Now this is very simple. We're going to prepare 100 cm cube, that is the volume of this compound, sodium triisocarbonate 4. What is this unit? we've laid emphasis. This is molarity. So if you don't see 0.05, for example, you could see if you don't see 0.05 molar, for example, you could see 0.05 mole per dm cube. So these units are the same. They are the same. All right. So now we have volume, molarity. Remember, each time you see the formula, know that this is molar mass coming up for you. So the formula we're going to use, without much ado, we already know, is molar concentration equals to mass concentration over molar mass. You see? So what is the molar concentration? We already know 0.05. So I have 0.05 equals to mass concentration. For us to be able to prepare 100 cm cube of this compound, we need to know the mass concentration, because we have to weigh. That is the first thing, mass concentration. Now the molar mass of sodium triisocarbonate 4, we have to calculate that. All right, the atomic masses might be given during your CBT, or it might not be given, so always know it. That sodium is 23, so I have to say 2 times 23, plus carbon is 12, oxygen is 16, so I have 3 multiplied by 16. So if you do this correctly, you should have 106 gram per mole. All right, so that's what you're going to put here. Can you see that? Just like we've done before, cross multiply. So if you do this correctly, x times 1, this times that, is going to be x will be equals to 5.3 gram. Now, if I asked you what weighing balance will be used to measure such weight, you know definitely it is the weighing balance that has an accuracy limited to plus 0.1. All right, meaning that the triple beam balance can serve, right? So that's by the way. So now that we've gotten the mass concentration, but remember there's something missing, that mass concentration unit is gram per dm cube. Can you see that? It is a concentration kind of mass. Now let's proceed. This is solving the question how you would prepare it, because you need to know the exact amount that you are going to add in 100 cm cube. That is our aim. So this value tells us that 5.3 gram will be in 1000 cm cube, because dm cube means 1000 cm cube. All right, so with that being said, if 5.3 will be in 1000 cm cube, right, how much will be in 100 cm cube? Do is cross multiply. 5.3 to multiply by 100 is 530 equal to x times 1000 is 1000x. So we divide both sides by 1000, divide both sides by 1000. So if you do this correctly, you should be having 0.53 gram. So it means that if you want to prepare 100 cm cube of this concentration of this compound, you need 0.53 in 100 cm cube of distilled water. And how would you achieve that? For you to achieve this, what you have to do is, depending on the volumetric flask, you need to have a volumetric flask that will support. Let's say I have a volumetric flask such as this one. Let's say this was 100 cm cube volumetric flask. Okay, first you have to dissolve this in a beaker. 0.53 gram goes in the beaker. Introduce it here, add some distilled water sufficiently enough to dissolve. All right, once it has dissolved, then transfer it to the volumetric flask with a mark. Once you carefully transferred it into the volumetric flask of 100 cm cube, for example, then you now start adding distilled water. Distilled water will start going in until it reaches this mark. So once you keep on introducing distilled water with your substance, sodium carbonate and sodium triisocarbonate 4, which is 0.53 gram to this place, and you make it to this mark, that means you've prepared 100 cm cube, okay, of 0.05 molar sodium triisocarbonate 4. So that is what it means. So you have to know how to do these calculations. All right, basically know the formula and know the unit. Right, let's go to the next experiment.